Hello, everyone, and welcome to Deep Talks. I'm Erin Broberg with Sanford Underground Research Facility, and I'll be your host tonight for Deep Talks. As always, we want to first start by thanking our sponsors. Our sponsors tonight are Crow Peak Brewing Company, RCS Construction, Northern Hills Federal Credit Union, and Chuck and Jolene Lichten-Wallner. You hear these names every single month, and we're so thankful for them for continuing to support these events and science outreach and education. So, as you guys know, Crow Peak Brewing Company will be sponsoring tonight's awesome door prizes. So we're going to go ahead and bring up that poll. Choose to enter yourself if you're on Zoom. So the door prizes tonight, we have 3 of them. One is a growler with 1 fill. Another is a 6-pack of Crow Peak's locally brewed craft beer. And the third is a gift certificate with a Crow Peak t-shirt. So all very good prizes. Now, this poll is only available to our Zoom webinar viewers. So if you're watching us on Facebook, be sure to join us next time on Zoom for a chance to win. As you're choosing to enter yourself, please note that you have to be 21 years of age or older, and you have to pick up the prize at Crow Peak Brewing Company in Spearfish, South Dakota. So if you meet all of those requirements, go ahead and enter yourself. We will randomly select a winner at the end of the event and contact you via email if you won. So I think we can go ahead and end that poll. All right, Matt's going to give you another second and then end it. All right, so tonight, as always, we would love to hear any of your questions. If you're joining us through Zoom, please use the Q&A function to submit questions. And if you're watching live on Facebook, you can add your questions to the comment section. Now, if you do participate in any of the polls tonight, or you ask a question on Zoom and Facebook, we have one other door prize that we're giving away. Got some surf swag for you. You can win a surf hat, which looks like it's going to be necessary in the Black Hills area pretty soon. We're getting a lot of snow tonight. So that's another thing you can win. All right, so tonight we are going to be learning about geothermal energy research happening right here at SURF. The U.S. Department of Energy's Enhanced Geothermal Systems Collab, or the EGS Collab project, is a group of researchers from 17 laboratories and universities who are advancing geothermal energy research across the United States. Since 2017, the EGS Collab has had a test site at SURF, first on the 4850 level and now on the 4100 level. This evening, we have 2 researchers with us from the EGS Collab. Hunter Knox is an earth scientist with the Energy and Environment Directorate at Pacific Northwest National Laboratory. Get a wave from Hunter. She works across the engineering field and geosciences to execute field-scale research and development projects. We also have Paul Schwering. He is a geophysicist with Sandia National Laboratories, with 15 years of experience spanning geothermal energy resources, geologic engineering, infrastructure investigations, and so much more. So both Paul and Hunter are incredibly passionate about their research, as well as education and public outreach. So we're really looking forward to this presentation tonight. With that, I'm going to hand it over to our awesome EGS Collab team. Thanks.
Thank you, Erin. Good evening, everyone. As Erin mentioned, my name is Hunter Knox, and it is my distinct pleasure to welcome you to our deep talk on harnessing the heat beneath our feet. Paul and I are going to start with some quick introductions and then jump to our discussion on geothermal energy and the exciting research being conducted in the EGS Collab project. First, a quick introduction. As Erin mentioned, I'm a geophysicist at Pacific Northwest National Laboratory, which is one of the federally funded research and development centers in the US. I've worked in these centers since the spring of 2012, and I've been actively involved in geothermal research since 2014. I've been part of the EGS Collab project since its inception, and I have been fortunate enough to spend substantial time in the Sanford Underground Research Facility and in the beautiful Black Hills. Now I'll turn it over to Paul.
Thank you, Hunter. And hello, everyone. Welcome. I'm Paul Schwering, alias Paultron, as some of you are aware. I'm a geophysicist with the Geothermal Department at Sandia National Laboratories, and I'm so grateful to be with you all here today. I've been extremely fortunate to work on geothermal research and EGS Collab with Sandia and with Hunter since 2017. Geothermal energy is a very compelling yet often challenging resource to harness. So advocacy and investment in the US and around the world, however, is enabling a wide variety of government, national laboratory, academic, and industrial institutions to collaborate and overcome the challenges to geothermal development. So this is what a lot of folks know that I call the geothermal good life, which of course has patent pending, as we all know. Hunter, will you please lead us off with some context on geothermal energy in general?
Will do. Let me get my screen shared. So we thought we'd start our conversation with you tonight with a little bit of a discussion in case there are folks in the audience that are unfamiliar with what is geothermal and how does it fit into the energy portfolio. And just so folks are aware, the picture on the right is from Utah Forge. We're going to talk about that DOE funded project as it relates to EGS Collab later on in the talk. Okay, the renewable puzzle. So we hear a lot about renewable energy, especially in the last sort of four years to the last decade. And when we think about the renewable energy, we think about biomass, solar, wind, and geothermal energy. Well, this diagram after Richter in 2020 shows how those four renewable energy resources contribute to cooling, electricity, and in heating. What we're hoping to give you some insight into is how geothermal energy in particular contributes to all three of those things: cooling, electricity, and heating. We won't touch so much on biomass, solar, and wind, but I'll put a plug in here for the other offices in the Department of Energy. There is active research that is done in all of the renewable fields, and if you're interested in it, you can find more information on the Department of Energy's website. So let's dive in a little bit further. First of all, geothermal energy is clean, and it's a perfect constant base load source of power. We're showing you on the left is a figure from a study that Blackwell led in 2011. And this is the temperature of the subsurface, or the earth, the rocks beneath your feet, at 6.5 kilometers. You might be wondering why we chose to show you the depth at 6.5 kilometers. And that's because standard drilling techniques used in the US and around the world today can easily reach this depth. So these temperatures are directly accessible using technology that we have today and can be used as geothermal resources. I will say that unfortunately, geothermal only accounts for about 0.4% of the net electricity generation in the United States, and that's about 3.5 gigawatts electric. So we're going to talk to you a little bit about what's standing in the way, what the exciting future is going to bring, and hopefully you'll walk away with a better sense. To do that, we have to teach you a little bit about geothermal energy by the numbers. So let's start first with a geographic discussion. If you look back at our slide, our previous slide here, you'll see that the temperature in the subsurface is much warmer in the western part of the US at 6.5 kilometers than it is in the eastern, with the exception of being West Virginia and parts of South Texas into northern Louisiana. So accordingly, right, our geothermal energy production comes from states nominally in the western part of the US. Leading producers of electricity from geothermal include California and Nevada. Nevada beats out California by producing more of its electricity, more of its share of electricity from geothermal, but California produces more geothermal energy in general. So then a little bit about geothermal resources. So not so long ago in human history, humans discovered that the Earth is a constant temperature at a certain depth. And so you can use this resource to either cool the air if it's hot outside before it comes into your residence, or you can use it to heat the air outside if it's winter time before it comes into your residence. So those are called low temperature geothermal resources or geothermal heat pumps. We'll go into that a little bit more next. As we come up in temperature, once we get to about 180 degrees Fahrenheit, we cross the boundary into what we would call a hot geothermal resource that can be used to produce power. So this is where binary geothermal power plants become economic. Everything up to about that point still has value, however. We can use those heat resources in food processing, in greenhouses, in concrete block drying, and other fabric and pulp drying activities. So we're going to talk about the highest end of this temperature scale, but keep in mind that geothermal resources can be used from everything from heating your home to powering the grid. So one last little slide on your geothermal overview. When we talk about geothermal resources, we talk about three distinct categories. We talked about geothermal heat pumps, which I just described. We then talk also about hydrothermal systems. You might be most familiar with hydrothermal systems and not even know it, because this is where the best hot springs are. So hydrothermal systems have natural permeability and natural circulation. So the water is coming through the subsurface and it's hot, and it comes up to things like hot springs, but it can be used for electricity generation. And then we have something called enhanced geothermal systems, which is going to be the focus for the rest of our talk tonight. In enhanced geothermal systems, the rock is hot, but it lacks the permeability or the connection between the boreholes to create power. So with that, I'm going to kick this over to Paul to talk to you a little bit about the Department of Energy and Geovision.
Thank you, Hunter. And I'll share my screen here and get us going. Okay. So what I'm going to describe here is part of the Geothermal Technologies Office mission that's within the Department of Energy, and some of the vision that's described particularly here in this Geovision report that was issued in 2019. Some highlights right off the bat here, and think about some of the context Hunter just described. So one thing right off the bat, this is non-technical, but optimized permitting to basically double the ability and timeliness of geothermal development would be a major change versus the business as usual that keeps geothermal kind of at bay. District use, so that's heat pumps at a larger scale, and district-wide heating installations. I mean, you're talking about tens of thousands of heat pumps and of those types of installations, and geothermal heat pumps from 2 million to 28 million. We're talking orders of magnitude here as part of this vision. Deployment reaching 60 gigawatts by 2050. And recall Hunter mentioning we're at 3.5 now. So again, order of magnitude and then some for some of the vision and initiative here. So through increased geothermal development, we could see a strengthened energy base, more stable power grid, and gain valuable economic and environmental benefits on the whole. So what's standing in the way? Now, I mentioned this before. There are other non-technical barriers that I'll note here briefly. There's public awareness. So this is what do the people want? What do they understand about geothermal energy, and where do they want it? What do they want it to look like? This is all part of where and that public awareness and really public initiative and action is what makes geothermal possible on one front. On the other front, as was mentioned, permitting, where 90% of these resources, particularly in the Western US, are on federal lands. So these can lead to long-term permitting applications that can really that are problematic as we get into the other aspect here, which is valuation or the economics of geothermal energy. There's also the levelized cost of electricity that doesn't really accurately represent geothermal's benefits as compared to other energy. But then also a geothermal grid, being able to have something that's more widespread and deployable. There's a lot of benefits here. We could give the entire talk about these aspects, but we're going to move on to some of the more technical side, but I want people to be aware of these aspects too. Technical barriers. So there's, again, a nice breakdown here. There's the exploration and characterization. So that's finding these resources. How do we detect them? How do we refine our understanding of how to optimally use or identify and access these resources? And then there's also, and that gets you to the next part, drilling technologies. This is one of the main pillars of the geothermal department at Sandia, improved drilling technology to increase our access and to lower our risks of drilling these wells. That is still an expensive activity. I'll jump over to the right on cross-cutting. So maximizing the use of geothermal resources through intersections with other needs. For instance, geothermal associated, for instance, with lithium mining, and lithium, of course, being a major part of batteries and electricity in general. But focusing here on subsurface enhancement and sustainability, well, that's where EGS Collab comes in, and some of these other aspects we'll talk about too. Subsurface engineering required to unlock EGS, that's enhanced geothermal system potential. So how do we find, we can find plenty of places with heat, as Hunter showed in that map, but how do we access that resource in a meaningful way for geothermal energy? And then how do we stimulate and maintain those reservoirs? These are some of the questions we're addressing. But right here, I want to make sure that people are aware of this, and I really appreciate GTO sharing this, these slides with me, so that I can present them to you, because there's a key mission to make known here, and that's that the GTO researches, develops, demonstrates, and validates innovative and cost-competitive technologies and tools to locate, access, and develop geothermal resources in the US. This will enable the development of carbon-free, flexible geothermal energy in both the electric and non-electric sectors, and consider these strategic priorities: driving towards a clean, carbon-free electricity grid with increased deployment of geothermal systems, decarbonizing by building heating and cooling loads, and then, oops, looks like I hit the exit button there. But the last thing I wanted to show here actually was what is the Geovision website, if I can get that pulled back up here. Yes, here it is. And here it is. So you can directly go to this website and learn more about Geovision, the benefits of geothermal energy, access the full report or the executive summary and various chapters within it. Please go have a look. You can simply look up Geovision DOE in Google and it'll pop right up. Okay. With that, I think we want to give our audience their first geothermal trivia question. There it is. Which two states produce the most geothermal energy?
Give folks about another 15 or 20 seconds. While we're doing that, I'm going to pull up our next set of presentation materials. Okay, let's go ahead and close the poll. So which two states, you might have heard me say this before, again, oh, the audience was paying attention, very good, 87% California and Nevada. For those of you who guessed New Mexico and Utah, New Mexico and Utah also have geothermal resources. I think they're working very hard to catch up to California and Nevada. So hopefully in the future, they'll be in the top lists as well. So let's jump in and let's talk a little bit more about the technical aspects of enhanced geothermal systems. So we refer to this as the geothermal moonshot. This kind of system hasn't been demonstrated for long-term application in the electricity sector. It is referred to in geothermal as an unconventional. So as I mentioned earlier, the subsurface is hot, very, very hot, but it contains little permeability or water to circulate between two wells. So lots and lots of people drive cars, and we generally know how a radiator works, right? We pump fluid in and it either cools or it heats, and then it comes out at different temperature. Okay, this is the same concept. So we take cold water, we pump it in an injection well. It flows through a set of fractures that act like a radiator, and it comes out of a production well hot. That hot steam or water then drives turbine engines and generates electricity. Very, very simply. There are all kinds of different power plants and all kinds of different ways to derive energy from it. But in general, that's basically how this works. So power generation at 7 kilometers, that assumes that we reach at least 150 degrees C, would allow for 5,157 gigawatts electric in this country. That is 5 times the total installed utility scale electricity generation capacity in the US as of 2016, which would heat and cool every home and commercial building for more than 8,500 years. This is why we're so excited about it. If we can make this work, right, we change the face of energy forever. Okay, here is what is standing in our way. So the US, as you have seen in my previous slides, has tapped less than 1% of the geothermal electricity resources, and the challenges are really this. Stimulation is poorly understood. Paul's going to tell you how we've been working on that. We get something called short circuiting or channeling. I think about these like thief zones. Some fractures take more fluid than other fractures, and that causes our radiator not to work very well. When this happens, we get something called premature thermal breakthrough, which means we cool down the rock that is right next to the fracture more quickly than we wanted to. And so we don't want that to happen. Sometimes we can't connect our 2 wells. It was certainly something we worried about a lot in our first experiment at EGS Collab. To drill these wells is not inexpensive, right? Drilling in hot crystalline rock is not for the faint of heart. And so these wells are deep and they're expensive and they have these extreme conditions, and therefore they require a significant investment. I'm going to tell you just very quickly before we jump into EGS Collab that we have a sister project. It's called Utah Forge. Utah Forge is in Milford, Utah, and it is the full-scale demonstration of EGS. So the objective for the DOE was to provide an underground laboratory to develop simulation techniques and tools that could operate for prolonged periods of time at these high temperatures. It's really an effort to extend oil and gas technologies into the geothermal sector, because oil and gas wells are not nearly as hot as geothermal wells. It provides a basis for both domestic and international opportunities. So it brings a collective of researchers together and gives them a common problem and platform to work from. And it is there to demonstrate the suitability of geothermal to provide electricity to the public and to provide a safety case to show that this can be done safely. So with that, I'll turn it over to Paul to begin the next part of the talk.
Thanks, Hunter. Getting my screen share going here on that one. Let's see. Here it is, and I'll just show this one slide and speak to it some here. So you'll recognize on the right side what Hunter was showing there as far as the full scale type application of enhanced geothermal systems. And where does EGS Collab fit in the path towards this? Well, I'm putting the statement out here, boldly crossing the valley of death. Now, the valley of death, Hunter also mentioned the geothermal moonshot, where we're heading here. But the valley of death, of course, is one of scale, simply put. So on the one hand, it can be demonstrated as what I'm showing on the left-hand side of the screen here is why sure, a hole can be drilled in a small sample, and a fracture can be stimulated. It can be imaged. We can put it under stress conditions using all kinds of really cool lab techniques and equipment. But one does that, and one can run various models and start to import or input rather parameters for a geothermal system. But can we really say, sure, we can do it at this lab scale, and then we can so something that's on the scale of centimeters or decimeters, and take that to kilometers. Before we go there, that's where EGS Collab steps in. And what we're showing here is actually a visualization of our first test bed that was on the 4850 with this array of wells that was drilled into the rock, and even with a representation here of targeted stimulations that are showing up. Monitoring wells, injection wells, we'll talk through all of this, but this was really the key point I wanted to elaborate on here before we dive into more about EGS Collab, is this is where we're residing in terms of the scale and trying to inform anything from Utah Forge and other demonstrations of EGS at the full scale, and how this can be applied and how it can work. So with that, okay, we'll take it to our next trivia question. True or false, permeability is a measure of how easy it is to fracture rock. I'll queue up my next set of slides here in the meantime. Okay, again, people paying attention there. That was false. When we're talking about permeability, it's actually a measurement of the ability for fluid transmissivity. That is how fluids can migrate. So good, folks are paying attention. This is great. All right. Well, with that, we'll jump into more about EGS Collab. So let me start up this next set of slides here. There we go. Okay. Ooh, that moved ahead on me. So here we are. There's two test beds to tell you about here. The first is EGS Collab Experiment 1, which was established on the 4850 level at SURF. So looking at a very simplified diagram of the many levels and really labyrinth that is the Homestake mining facility, we're right here in kind of towards the middle of how deep down to the 8,000 level Sanford underground research, or the Homestake mine, went. And the 4850 is where the hub of activity is with respect to Surf Underground Research Facility. And we found ourselves in the Poor Man Formation there. So we're getting into Proterozoic Stratigraphy. So Proterozoic, what do I mean? Why we're talking about before life on Earth started. We're at the upper hundreds of millions to even billion years of age when we're talking about some of these formations here. And so and images up here include some of the core from the Poor Man Formation there, and even the drilling inside the drift on the 4850. So the objective of experiment 1, which was to investigate hydraulic fracturing. So naturally, I use my hands anytime I talk about this, because we're talking about opening up fractures, popping them open, and that's what I'm depicting on this left-hand side here. So opening up a fracture to increase that permeability, that fluid flow inside the formation. And what you're seeing in the upper right, these images are an incredible amount of equipment and an amazing team that instrumented these many boreholes. And what we're showing here is a view from above on this schematic of the 4850. So that's the drift with primary injection well with these targeted stimulation zones here, yellow monitoring wells, which I'll describe in a little more detail, and a targeted production well. That is a well where the fracture would intersect and give us our system. It's important to realize what we're doing here is basically everything in EGS at a smaller scale and also without high temperature. Experiment 2. Now we've moved up a level, the 4100, so we're above a lot of the action that's taking place on the 4850 these days. And yet we also moved in a direction closer to the Yates shaft, which actually put us a little lower in the stratigraphy section here. We're in the Yates member of our geologic section here. Again, so much effort is going into how we understand and characterize the rock mass here. We've got core being evaluated in mass here at the new warehouse facility. Our team of scientists here doing wireline logging of these boreholes, again, to understand these rocks in enough detail that we can do these fracturing exercises and start to predict how that's going to go. The difference here, so what is experiment 2? We're trying to investigate shear fracturing. So instead of popping the fracture open, you're trying to displace it. That is to create some motion between on either side of a fracture to, again, increase permeability, with one advantage of shearing being that may in fact help maintain the fracture aperture, that is the opening, that pathway of fluid flow. We've again deployed an array of wells. We're showing red wells here that are our primary test wells, with a central one for stimulation, and several that may in fact be intersected by a shear fracture, in addition to having our yellow monitoring wells that kind of cage the whole system. And the setup on the 4100 is quite remarkable, with members of the EGS Collab team showing off a setup that took many months of planning, a whole lot of infrastructure input from SURF, and a simply incredible job of making a remarkable array of equipment fit into this drift. So we're talking about all of this, stimulating the rock. Well, where does that fracture go? how do we find out, okay, sure, we've got shear, we've got, how do we know we've achieved what we've set out to do? Well, that's where geophysics comes in. And as we mentioned in our intro, Hunter and I are both geophysicists. Now, this is a nice depiction from USGS, how we wish geophysics worked, why we want X-ray vision to see what's going on inside the rock mass. But of course, we can't really see what's going on. So we detect signals that give us a picture based on different physical parameters and characteristics of the subsurface to tell us what's happening underground. This is analogous to modern medical practices, for instance, an ultrasound or a CT scan. And just like in those practices, well, there are ambiguities. And so a lot of this is subject to interpretation and intersection and assessment of information. So that's what we set out to do in EGS Collab. We have a wide array of geophysical monitoring parameters and systems, and I'll touch on a few here. One of our primaries is microseismic. And when I say microseismic, you may think of seismic as, say, seismicity associated with, say, earthquakes. You may have heard like a magnitude 4, which is maybe perceptible, to magnitude 6s, which can create quite a bit of shaking. We're talking about at the microseismic level, so orders of magnitude small, to the point where we can't feel or even hear these types of events, but we can detect them with really sensitive instrumentation. And when we monitor these things in real time, why we find that as, for instance, a fracture propagates, as these things open up, the events form these planes that we can interpret as, aha, that's where our fracture went. That's how it evolved over time. And that helps us maintain and image our experiment. We also have another tool in the toolbox, electrical resistivity tomography. So electrodes that are down the hole that are simply transmitting and receiving electrical signals. And again, monitoring this with time, along with inflow, outflow, and basically seeing the behavior of our wells on the one hand, but tying that to these electrical resistivity changes with time that tell us things about fractures that are opening, even places where there's kind of a shadow effect where things seem to close off depending on where you stimulate, how you stimulate, what sort of pressures and flow rates you're working with. So we've learned an incredible amount from this tool as well, in addition to microseismic. Basically, we can tie so many of these things together. We also have distributed temperature, that's fiber that's been run down these wells, and we have and we find locations where, for instance, fractures intersected those monitoring wells, and that tells it that's another place. Oh, that's where our fracture went. That's where our fracture went and when. And tying that with microseismic, and we even got to take downhole camera footage during flow testing, which we got these really cool, I like to call them car wash videos of water entering the production borehole that from that injection on the other side. And we tie all this together along with our stimulation and flow parameters. And again, it starts to tell the story of how our stimulation worked, and to monitor our flow testing. So where are we now? We're actually in the process of instrumenting the 4100, which includes everything from fiber, microseismic, ERT, and in placing these in the wells. We've got them instrumented, and we're getting them ready to go for being grouted in place. That is so that these things are well bonded to in the subsurface to get the best signals that we possibly can. And again, we've got a remarkable amount of instrumentation that the SURF and the EGS Collab team have established here on the 4100. So with that, we'll toss it back over to Hunter.
Thanks, Paul. So let me pull on a couple of those threads because Paul made that seem pretty simple. We came up as researchers, we always have names for our test beds, and we decided that the test bed on the 4850 was indifferent. And so when we got our data the first time, I'm showing you on the right-hand side of the screen, a plot of all the fractures that we could find in the core and in our geophysical measurements. And we thought, okay, well, that's kind of a mess. What are we going to do with that? And which ones of these fractures will matter, and how can we, how can we make this work? Remember, we haven't put the fracture between the stimulation well and the production well yet. So there's lots of natural fractures. There's this complex rock fabric. How is this going to affect us, and what are we going to do? So we put our heads together, and we decided there was one important fracture. Or it was at least the most important fracture. And so we're talking a little bit today. I'm going to show you a little bit of our data, dive in a little bit more to Paul's discussion, but we're going to talk about the stimulation that we did at 50 meters depth. And we drove it, if you can see my mouse here, from this location on the red borehole to the location on the blue borehole. And it interacted with this natural fracture. Now, Paul already showed you this awesome slide where we saw the jets, but this is how we confirmed how that hydraulic fracture interacted with the natural fracture. We could see that we got fluid flow through both fractures, and we could actually see the production of water from both fractures in the borehole. So this is our positive confirmation. Remember when we talked earlier, step one for EGS Collab is connect the two wells. This is the first step for an EGS system too. So once we've done that, now we need to test our circulation. And that just means we're going to flow water in one well and produce it out of another well for a very, very long time. I don't think any of us were really prepared for the duration at which we needed to do this. I will share with you some funny science anecdote that we spent the first 30 days of this on a Zoom call together, 24/7. And there were lots of panicky moments at 3 o'clock in the morning. And then we sort of settled into a rhythm. And so we monitored this system for nearly 12 months. And luckily we have a bright and capable engineering crew that built a system that could handle this in a number of ways. So we had 4 primary asks from them, and that was that the system be able to be remotely commanded and controlled. So this is like running a science experiment from your living room, which is pretty great. And it needed to be interfaced and integrated with all the geophysics that Paul just talked about so that we could make the important observations. We had 100 continuous measurements in just the stimulation so that we could check on the state of health and just everything that was going on downhole and in the drift. And we needed incredible accuracy. All of that data, we're going to show you how you can access it, but all that data is a product that's delivered to the American taxpayers. And so we take great pride in the fact that we were able to do this for such a long time. I'm going to say one more note. You just heard me sing praises for the engineers and the visionary instrumentation specialists that work on EGS Collab. This kind of effort does not occur without an army. And these are the people that have contributed and participated in the EGS Collab team. Aaron mentioned early on that there were 17 national labs. There's also industry and academic partners. And I'll say this too, I think Stephen Gould said this best, creative work in geology and anywhere else is interaction and synthesis. Half-baked ideas from the bar room, rocks in the field, chains of thoughts from lonely walks, numbers squeezed from rocks in laboratories, numbers from a calculator riveted to a desk. He dated himself a bit there. Fancy equipment that's usually malfunctioning on expensive ships or in deep mines, cheap equipment in a human cranium, and arguments before the road cut are requirements for good collaboration and solving the kinds of problems and challenges that are before us in geothermal energy. So a collaboration was the most important ingredient in this recipe, and I think the team has done a good job of showing the value in that. So with that, I'm going to kick this back over to Paul momentarily. We're going to show you some resources and then one final trivia question.
That's right. Thank you, Hunter. And I'll actually start even briefly here with just a quick field trip to the 4100 here. So we have Vince Vermeulen actually speaking with Aaron Broberg here and describing some of the site. And again, I always like to emphasize this part. I think a lot of people worry about geologists because they're by the side of the road waving their arms looking frantic, but no, we're just really excited because we're trying to describe what's going on with the rock. Then on the other side here, we're looking at some of the wells, these instrumentation feed-throughs that we've been talking about. This is one of our wells that will be a production well, but it's currently instrumented with all this fiber you can see starting to run into the wellhead there. We've got these many flow meters, valves, an incredible array of instrumentation for this autonomous operation that Hunter was describing there. And meanwhile, all of this can be controlled right there on site, but also, as Hunter was mentioning, from our living rooms as the experiment can go on. When we talk about stimulation, this is one of the key tools we use. This is a packer, so those rubber bladders on either side there can isolate the hole and gives you a place to inject that fluid pressure. And we've got all of this hooked up, and so this long umbilical will guide down the borehole and transmit all of the fluid pressure and information we need as the project continues. So, yeah, the resource that I wanted to share here briefly too, for everyone's benefit is, let's see, right here. So here's one, on the one hand, the EGS Collab wiki on OpenEI. Have a look. Again, you can dig into so much more detail and watch some of the exceptionally cool visualizations that the EGS Collab team has put together, and even a kind of a scale look here at our footprints on the 4850 on one hand. That's again a look at this previous test bed for experiment 1 that we had, but then also moving up to the 4100 where we have this next test bed. I also want to highlight the geothermal data repository. So as Hunter was mentioning, this is where this data is living with a lot of context, images, and so forth. And this is the data for people to use for modeling, for validation, and for context in EGS applications and others as folks can see fit. So with that, I think we're at our last trivia question here. All right, the difference between the test beds on the 4850 and the 4100 are.
Give folks another couple seconds and then we'll close the poll and see how everybody did.
Well, great job, everyone. Yes, all of the above is the correct answer when it comes to rock type, fracture, experiment type, experiment 1, experiment 2, shear and hydraulic fracturing, and then the length of the cage ride too is a factor. Okay, well, with that, thank you all so much for your attention. We're going to pivot to the Q&A from the audience, which people can input in the Q&A field. Meantime, I'm briefly going to share one more aspect of geothermal that Hunter and I are both very excited about. That is This is Women in Geothermal, or WING as it's known. You may have noticed Hunter and I are wearing our WING pins. Hunter and I are longtime members and advocates of WING, and I also have the privilege personally of serving on the WING Global Operations team. The website is womeningeothermal, all one word, .org. And the key steps are laid out right here on the home page, okay? Learn about us, donate, and join WING, become a member. It's all very easy. Joining WING is free. And I want to highlight this key point here, that this is not a women only, nor just a geothermal scientists only group. In my opinion, equity in the workplace is an initiative that's best built on a foundation of equal representation. Okay, we all have to have the courage to show up, and we all must care enough to help each other out. So please do go to the website, learn about the many ways you can participate in WING. Well, thank you very much, everyone. Aaron, I think we'll hand it to you for perhaps the first question.
Yeah, can you guys hear me okay?
Gotcha.
Got you loud and clear.
All right, so we have a lot of questions. I'll let you guys decide who takes which one. But the first one I think is very important. The question is from Beth on Facebook. She asks, wouldn't drilling cause instability in the ground, and how big would these holes be? So a concern about safety.
Yeah, that's a great question. I'll field that one, Paul. So boreholes are drilled probably all over, certainly all over in the US for various purposes. Some are water wells to tap into aquifers to derive drinking water. Some are for extracting petroleum products, and similarly geothermal wells. These boreholes tend to be in the geothermal sector 8 to 10 inches in diameter. They do not cause an instability in the earth. Actually, a borehole causes the stresses around it to sort of strengthen the earth right around it. So no worries about collapsing in from the surface or collapsing in the borehole.
Awesome. Another question is, how much smaller are the test borehole systems in the Collab project compared to what is envisioned for a full EGS system? And what do you expect any challenges in applying results from Collab to a full EGS system?
For sure. And so on the one hand, the difference in scale there, so in terms of footprint, so we're occupying a space that's about the length of a football field in that drift, and you know, these wells are tens of meters long, basically, or tends to a couple hundred feet. Basically, whereas when you're talking about the full-scale EGS application, you're talking about wells that can be many kilometers or thousands, or perhaps even a 10,000 or more foot well. So that's, and there's also a spatial consideration there too. A geothermal field footprint tends to be, you know, that's something you would measure in acreage, not say a single football field. And so that's kind of the different types of scale we're talking about there. Now, the second part was the challenge, and yes, there are definitely challenges of scale based on, you know, either whether it's rock parameters, fluid and temperature, all of these things. There are always challenges with these, but again, that's even one of the more important reasons, I think, to be in this middle place, this intermediate scale test bed at EGS Collab, so that we're not just taking the gap from, you know, handheld samples to tens of thousands of feet wells.
Great. And I'll add to that question a bit. This question is from one of your collaborators, Pat Dobson. Given the complexity found in the EGS Collab testbed, how do you envision being able to successfully design and deploy EGS resources over a large range of geologic conditions across the country and around the world? And there are a couple other questions like that, talking about different regions and how to apply in places that are quite different.
Yeah, we'll have to thank Pat for that question. That's a tough one. So I think let me make a tie for you. We didn't show a lot of these results. One other very important part of the EGS Collab community is the modeling community. And you saw their names sprinkled throughout our presentations. But what we're trying to do is perform experiments that inform models that then can be used to project results at other locations. So it's really our tie to our modeling component that helps us transfer these learnings to other rock types or other geologic settings. That sounds, Pat will not be satisfied if I know him well with that answer. But I will say this too. I think every time we do this, we learn something new about the behavior in the earth. We will build enough experience to make this work successfully. So there will be best practices. There will be new ways to monitor or evaluate fractures that come out of this kind of research. And there'll probably be new models or statistical methods that help us understand our systems as we move forward. So it's sort of, rising tides raises all ships. And so I think this research just helps build that foundation, and it will translate through a variety of connections.
Yeah, and that's such a key point too, as far as a lot of what we're doing in the field here. Well, most of the hypotheses, the things we test, the way these experiments are run, come from models that say, well, here's what we think can happen. We're testing a hypothesis that came out of a numerical simulation or a model that tells us, well, here's what we think will happen. And then we go forth and see what reality gives us. So on the front end is that numerical simulation input. And on the back end is then taking those learnings and expanding them to that next scale at the full scale of EGS.
So great answers. We had a couple of people paying close attention to the heat map that you showed at the beginning. One of the questions is, what is causing the area of higher temperatures in Southeast Texas and Louisiana?
I think that's a really good question, and I don't know the answer to it. I don't know if you do, Paul.
Yeah, I'm not sure, and so I'm not sure what's behind that. The trace, as I understand it, I mean, that's where there is so much oil and gas exploration, of course, and so those basically those anomalies, that temperature field that you're seeing there, that came from oil and gas exploration that revealed those trends. What's exactly behind that particular trend, I'm not so sure.
Yeah.
Sure. Well, another question about that map is coming from Marcus Horn. He asks, South Dakota and the Black Hills seem to be kind of the colder areas in the US. What makes surf a good place to do the research if the rock is not hot?
I can take that one.
Oh, sure.
So the drifts inside surf allow us to access the same rock under similar stress conditions that we would access through deep wells. So it's actually an economics question. It is much more economic to do the kinds of experiments we're doing in a place like Sanford Underground Research Facility or in deep mines than it is to emplace our boreholes from the surface.
It's one part economic, and I would also submit that that's also part of the scale thing too. It is very hard to drill very long, very tightly spaced wells and then be able to image and instrument those. Whereas if we're right there underground in the correct stress conditions, as Hunter was mentioning, why then we can drill these much shorter boreholes at the intermediate scale that we intend to.
Awesome. And we've got a few more questions left. So if I can keep you guys a bit after 7, we'll be very happy to continue into these. Some very good questions here. One question is, could you discuss the environmental concerns with current oil and gas fracking and how they may relate to fracturing for geothermal heat energy extraction?
Yep, that's a key question here. And so one thing I'll clarify too, as far as the experiments that we're running at SURF, we've been using simply water So that's been our working fluid for injection production, and really the only things we've been changing there are either the the electrical conductivity of the water, or also by and also temperature by cooling the water and testing that thermal effect. Now, as far as hydraulic fracturing practices go, that's one of the questions out there, is what types of techniques and what's that going to look like when you're stimulating these wells at a geothermal scale and in a geothermal system. So everything from the seismicity associated with fracturing is something that's intensely monitored, and that's one of the things that we're also bringing from EGS Collab is best practices for monitoring and maintaining these systems, as for instance your hydraulically fracturing.
Great. Okay, after that one, I'm going to toss you an easy one. Which EGS site, the 4850 or the 4100 level, is your favorite?
Oof. You know, I gotta say, and once we had the 4100 instrumented the way it is, seeing that facility now, it is an incredible sight to behold. And the 4850 blew me away when we first got that set up, when we first got to work there. I didn't think it could get any better than that. But the 4100, after all the work and really a lot of the lessons learned too from the 4850, it really is quite literally and figuratively our level up, I think, in test beds. But that is my opinion.
I agree.
Great. Okay, another question is, extracting heat from rock to heat our homes is very cool. Can you comment on the concept of storing heat or energy in rock?
Yeah, I can field that one. It's an excellent question. There is lots of work going on inside the Department of Energy to understand how to build batteries out of something other than lithium. And there is an idea that you can use the earth to store heat and then extract it when you need it. You might see this implemented in things like mines, where you could heat up the drifts and things like that. But you might also see it in sort of shallow subsurface systems. So there's absolutely a possibility that you could pump. Let's say you had a concentrating solar tower, right? And you have all this excess heat that is generated from it, that you could pump it into the subsurface and store it for later use. So that's a great question. The earth is a good storage facility for things like heat. So I think there's exciting research to come.
Great. And then we have two questions about time frame for commercialization. One says, what is an estimated timeline to realize practice application at a noticeable scale in the power grid?
Well, to put that into context of EGS, I mean, so seeing deployable EGS, that I think harkens back to the Geovision story there, which is laying out a path that's on the scale of the next few decades. So up through 2050 of seeing that deployment realized, where again, it's we're talking about order of magnitude level increase in geothermal. So I would say stay tuned even over the next few years as the results from EGS Collab come out, from Forge come out, and field demonstrations continue to prove out as this goes forward.
Great. A question from Stephen asks, Paul mentioned that one of the biggest limiters of geothermal are current drilling techniques. What sort of improvements can be made to drilling to make it more practical?
So there's a lot of technologies that are at work there. So on drilling itself, being able to drill in these high temperature and high pressure environments, it's really hard on tools. And so that's one of the areas is as being able to withstand those geothermal conditions, which can be very rough. On top of that is being able to articulate these wells in these conditions. And when I say that, I mean really targeting, like is done in oil and gas, to even going to horizontal drilling to access more of the resource and protect and more of the fractures across them. So these are the sorts of technologies that are both they're mechanical, electrical, and also and geophysical too, for that matter, getting this information from the surface up to operations to steer some of do anything from steer some of this live, but also maintain these your tools and integrity in these really tough environments. Particularly, another place is lost circulation zones, and that is another. And what that is where you lose pressure because you've hit a high fractured area. There's myriad challenges in drilling geothermal, and but we're getting better and better at it.
And just a quick kudos, Utah Forge drilled a borehole. You can look this up on the internet, and they finished in record time. And so I think we're all cautiously optimistic that perhaps we have found the right tools in the toolbox to address some of these challenges. But Utah Forge did an incredible job in drilling their last borehole, and yeah, round of applause to them. It's certainly a crowning moment.
Well, I'm glad you brought up Utah Forge, because one of our questions is when does Utah Forge begin to produce energy? And then will it feed power into the grid, or is it strictly for research? And how long will it operate? So if you can keep those three questions in mind, talking about Utah Forge.
Yeah, I don't believe there are plans, Paul, you can correct me, but I don't believe there are plans for Utah Forge to produce electricity. It is really considered a subsurface testbed to understand stimulation and technologies. The first round of proposals was funded last year for people doing research at that facility. And I believe the next round of proposals will be requested next year. So there's at least 2 rounds. I think you'll see research come out of the Utah Forge site probably over the next 10 and maybe even 15 to 20 years.
Awesome. All right, I think we have time for 2 more questions, then we will wrap up. One of the questions is, how do you prevent the water that you are pumping into the rock from seeping back into the laboratory or into the drift?
So that's where a lot of our instrumentation comes in. So on the one hand, there's the well control aspect here that I think is being invoked a little bit, which is, while you're pushing water down, how does it not just come back up the well? Well, that's where your packers come into place here. You have a packer above that's pressurized and basically squeezes out any pathway back up the borehole, and likewise one below, and you have this interval where you're injecting and inducing a fracture in between those 2 packers. So that's one aspect. And then the next is, well, that fracture propagates, and again, I think that's the other aspect here, is we're monitoring our fracture as it extends. And so that's another thing we don't want to do, is extend a fracture too far, so to speak. We want them to be right where we're working in our test bed between our wells, and that's basically how we keep the experiment working within the test bed rock. I think those are kind of the 2 key parameters there.
All right, and so our final question is, what is done with all of the drilled out materials?
The disposal of the, so in this case, in the case of EGS Collab, so all the returns from drilling. So EGS Collab is remarkable because every one of those boreholes, so you're talking several thousand feet, have all been cored. So all of that core was pulled in 5-foot intervals, and is actually located at the surf core repository. Now, we do get cuttings, of course, from blading through the rock, and that has to be disposed of either in a location that's suitable at surf or usually somewhere on the level, based on where things need to go. But dealing with drill cuttings, no matter where you're doing it, on the ground, surface, underground, that always takes a lot of planning and coordination.
Great. Well, thank you both so much. One last minute question that I can answer is, some people are asking about a compilation or gallery of EGS Collab pictures. Sanford Lab does have a photo gallery, and we can make sure it's up to date and share it on our social media channels tomorrow or this coming week. So watch our social channels and we'll be sure to share some of those photos, because they are awesome and you guys have completely transformed that drift. It looks amazing. So we'd love to share that. All right. And with that, I want to thank you so much, Paul and Hunter, for joining us. As you may know, if you've been attending our deep talks, you will get the famous Ross Hoistroom print, or Ross headframe print with the Black Hills, as a special thank you for being willing to give up your time and to go overtime to answer all of our audience's awesome questions. Thank you again, audience, for being so curious and attentive. You did really good on the trivia questions, so we can tell you were paying attention. I want to say one more thank you to our awesome Deep Talk sponsors and to the Surf Communications team that makes these events possible. We'll also remind you to join us on Thursday, February 10th for Deep Talks, a love-heat relationship with Surf's Education and Outreach team. When you leave Zoom, you'll be given the option to take a survey about your Deep Talks experience. And in that survey, there will be a link to register for the February event. So we've tried to make it really easy for you. We'll also be sharing that information on our website and social media channels. We're always trying to make these events better. So please do leave some feedback on that survey. A recording of this talk will be shared on Facebook, Vimeo, and YouTube channels. So feel free to share it with a friend who might have missed the event. Thank you so much for joining us tonight. And thank you, Paul and Hunter.
Thank you. Have a blessed night.